Hey everyone, welcome to today's Explainer. We're going on a high-energy geographical tour of the middle and bottom blocks of the periodic table. If you're prepping for exams, or just want to understand the hidden mechanics of the elements that literally build our world, consider this your ultimate cheat sheet. We're going to break down the complex chemistry of transition and inner transition elements into clear, manageable steps. Let's get right into it. Here's our roadmap for today. We'll start with mapping the periodic table, check out the D-block rebels, explore the superpowers of transition metals, head inside the F-block basement, compare the D and F blocks, and wrap up with some essential exam takeaways. All right, Section 1, Mapping the Periodic Table. Let's get our bearings. So why are some elements banished to the very bottom of the table? It's kind of a geographical mystery in chemistry, right? Why does the F block live down there in the basement while the D block gets to rule the bustling center stage? Well, it all boils down to the specific orbital that receives the atom's absolute last electron. For the D block, those electrons enter the D orbitals, putting them right smack in the middle, spanning groups 3 to 12. But for the F block, the electrons drop into the deeper F orbitals, which structurally separates them out at the bottom. Now, what's really interesting is how we actually define these central elements. A transition element is formally defined as one that has partially filled d orbitals in its atomic or ionic state. But listen up, because there is a classic absolute trap of an exam question right here. Zinc, cadmium, and mercury are physically sitting in the d block, sure, but they are technically not transition elements. Why? Because their d orbitals are completely filled with 10 electrons, no partially filled orbitals there. So definitely do not let that trick question catch you off guard on test day. Moving on to Section 2, the D-block rebels. The thing you've got to know is that not all elements play nice with the standard electron configuration rules. Take chromium, for example. Based on the usual pattern, you'd totally expect its outer shell to end in 3d4 4s2, but its actual configuration is 3d5 4s1. Why the switch? Because a half-filled D subshell offers incredible thermodynamic stability. And copper, it pulls the exact same trick. It steals an electron from the s orbital to become 3d10 4s1, achieving the perfect stability of a fully filled D subshell. It's kind of like a perfectly balanced seesaw. They're breaking the standard rules just to reach a more comfortable, stable state. Up next, Section 3, Superpowers of Transition Metals. Let's dive into superpower number 1, variable oxidation states. Unlike your standard S-block metals that usually just toss away an electron or two and call it a day, transition metals are highly flexible. Because there's just a tiny energy difference between their outer NS electrons and their inner D electrons, both layers can get involved in bonding. Look at manganese. It can shift its oxidation state anywhere from +2 all the way up to +7. Iron can comfortably sit at +2 or +3. This molecular flexibility is essentially the foundation for almost everything else these elements can do. And building right on that flexibility, we have superpower 2, catalytic properties. Thanks to those variable oxidation states we just talked about, transition metals can easily form temporary intermediate compounds. This makes them absolutely phenomenal catalysts. They speed up essential chemical reactions without actually being consumed themselves. To ground this in the real world, iron is the crucial catalyst in the Haber process for making ammonia. That process literally keeps half the global population fed through fertilizer production. And vanadium pentoxide? That's the star catalyst in the contact process for manufacturing sulfuric acid. But it doesn't stop at catalysis. Check out superpower 3. Visually, these elements are just stunning. Because their d orbitals are only partially filled, electrons can jump back and forth between them. We call these DD transitions. When they jump, they absorb certain wavelengths of light, meaning they emit these brilliant colors. Copper 2+ gives us a striking blue. Iron 3+ is a rich yellow-brown. Plus, and this is super important, because these transition atoms are relatively small, pack a high charge, and have vacant orbitals, they love forming massive, complex structures. They also seamlessly mix to form incredibly tough alloys. Their atomic sizes are so similar that you can just mix iron and carbon to make steel, or copper and zinc to make brass. All right, let's head downstairs. Section 4, inside the F-block basement. Down in the basement, we first run into the lanthanoids, also known as a 4F series. These guys run from cerium to lutetium, which you absolutely need to know here. Their default, most common oxidation state is a solid +3. They're also strongly paramagnetic, meaning they're drawn to magnetic fields. And just like our transition metals, they form brilliantly colored compounds, though here it's via FF electron transitions. You actually rely on these elements every single day. Neodymium is used to make ultra-strong magnets, cerium is essential for glass polishing, and other lanthanoids provide the glowing phosphors that light up your TV and smartphone screens.
Now, a massive concept for your exams is a phenomenon called lanthanoid contraction. As you move across the 4F series from lanthanum to lutetium, the atoms actually gradually shrink in size. But why? Well, it's because the 4F electrons are terrible at shielding the outer electrons from the nucleus. Think of it like wearing a jacket that's way too thin to block a cold winter wind. As you add protons, the positive pole of the nucleus keeps increasing, and because that F electron jacket is too thin to shield the outer electrons, the entire atom just gets pulled tighter and tighter, shrinking its overall radius. Right below the lanthanoids, we find the actinoids, or the 5F series. If the lanthanoids are the quiet, steady workers, the actinoids are the wild ones. They display a massively wide range of oxidation states, spanning from +3 all the way up to +7. But the biggest takeaway here is their energy. Every single actinoid is highly reactive and universally radioactive. They form chemical complexes much more readily than their lanthanoid neighbors above them. You probably know them best for their immense power output. Elements like uranium and plutonium are literally the lifeblood of nuclear fuel and atomic energy worldwide. Moving right along to Section 5, comparing D and F blocks. A crucial goal of this explainer is making sure you can rapidly tell these two blocks apart. The D block sits right in the middle stage, boasts wildly variable oxidation states, has moderate magnetism, is rarely radioactive, and is found abundantly in the Earth's crust. In stark contrast, the F block is tucked away at the bottom. Their oxidation states are heavily anchored at +3, they exhibit very strong magnetism, radioactivity is incredibly common, especially with those actinoids, and they are much rarer to find naturally. Keep this head-to-head contrast firmly in your mind. Let's wrap things up with Section 6 essential exam takeaways. First up on our cheat sheet, the vital compounds you simply must memorize. Number 1 is potassium dichromate, K2Cr2O7. This is a remarkably strong oxidizing agent, and you'll recognize it immediately in the lab by its distinct bright orange color. Next is potassium permanganate, KMnO4. This is another incredibly powerful oxidizing agent, legendary for its deep, rich purple color. Know their chemical formulas, know their vibrant colors, and remember that they are both absolutely fierce oxidizers. Next, we have the mathematical formula for calculating the magnetic moment of an ion, mu equals the square root of n times n plus 2. This is measured in Bohr magnetons, which is simply the standard unit used to express the magnetic moment of an electron. In this equation, n stands for the number of unpaired electrons. It's really that simple. Count the unpaired electrons, plug that number in for n, do the math, and grab those easy numerical marks on your test. All right, here is your rapid-fire exam survival guide checklist. 1. Memorize those electronic configurations and the most common oxidation states. 2. Understand exactly how poor electron shielding causes the lanthanoid contraction. 3. Know that DD and FF transitions are the physical origin of those brilliant chemical colors. 4. Practice your assertion reasoning questions and those exact magnetic moment numericals we just looked at. And finally, number 5. Always remember the chromium and copper stability exceptions. Direct your final study efforts right here, and you're going to ace this material. As we close out this explainer, I want to leave you with a final thought straight from our source material. The D and F block elements form the backbone of modern chemistry, from industrial catalysis to nuclear energy. You know, these aren't just abstract letters and numbers on a page to memorize. These are the heavy-duty, real-world elements that literally power, build, and sustain the modern world around us. Which brings us to a rather provocative question for you to ponder. What future technologies might be unlocked by mastering these atomic backbones? From next-generation batteries and stronger architectural materials to limitless clean nuclear energy, the applications are practically boundless. I'd encourage you to look beyond the exam, stay curious, and imagine what we can build next with these incredibly powerful tools. Thanks for joining me to explore the chemistry of transition and intertransition elements, and as always, keep learning.